Hey there, geometry class. I hope you really appreciated that geometry quiz the way I'm going to appreciate it this weekend when I get to grade it. In this lecture, we're really going to be looking at 4 units, the sections 4.5 through 4.9 in your textbook. We're going to skip 4.8. We're going to save that for a little more theoretical stuff, and you're definitely going to hit that much harder in Algebra 2. So the key points in this lecture are: how do we know triangles are congruent? What are the shortcuts? What does it mean when triangles are congruent? And this is the really important practical stuff that has gotten us to the new world. And the third one is, let's just look at some special triangles like isosceles triangles and equilateral triangles. So you may recall in the previous lecture we talked about triangle congruence. And again, when polygons are congruent, all their corresponding sides and all their corresponding angles are congruent. And if you have those features, then you know that those figures are congruent. The problem with this is it's at least 6 things that you have to prove congruent. So are there shortcuts? And of course there are shortcuts. And so that's what we're going to talk about now. The first shortcut is postulate side, side, side. And for some of you, we did the straw example in class, and you saw that if 3 lengths of a triangle are the same, you can only make 1 triangle out of those 3 lengths. So again, this is a 2, a 4, and a 5-inch piece of straw, and everybody's triangle looks exactly the same. So again, this is a postulate. This is not something that we're trying to prove. We're going to accept it as true without proof. So what does this mean in the real world? Well, why is triangle ABC congruent to triangle CDA? Well, the answer is actually really simple. If we know all sides are congruent, then we know those 2 triangles are congruent by the side, side, side postulate. Well, here it is. AC is congruent to itself, to AC, and that's by the reflexive property. So with that property in mind, reflexive, now you know that all 3 sides are congruent, all corresponding sides are congruent, and therefore those 2 triangles, ABC and CDA, are congruent by side, side, side. The next one we want to look at is called side, angle, side, and the key here is that you have an included angle, and an included angle is the angle formed by 2 adjacent sides of a polygon. So again, B is the included angle between sides AB and BC. So this is what this postulate looks like. And again, if you've got a side, angle, side in order, congruent to another triangle's side, angle, side, then you know those 2 triangles are congruent. And again, the letters SAS are written in that order because the congruent angles must be between pairs of corresponding sides. So here's what it looks like. Use SAS to explain why triangle ABC is congruent to triangle DBC. And it says, oh, well, BD and AB are congruent, and those angles are congruent. And hopefully by now you say, wait a minute, isn't BC congruent to BC? And of course it is, yes. So again, I wrote BD. Yikes, Mr. Rising. Scary stuff there. BC is congruent to itself. And let me label this right now to make sure that that's really clear. So that is congruent to itself by the reflexive property. So now we have a side, angle, side, a side, angle, side. And therefore we can use SAS. Now, just like an included angle, an included side is a side between 2 consecutive angles. So PQ is the included side between angle P and angle Q. All right, seems to make pretty clear sense. So let's try this one. The postulate angle, side, angle, right, states that, again, only 1 triangle can be formed if I'm given 2 angles and an included side. Now what's interesting about this is you get some really good real-life problems in trying to determine where things are. Let's take a look. A mailman has to collect mail from boxes at locations A and B and drop it off at the post office C. Okay? Does the table give enough information to determine the location of the mailboxes and the post office? All right, so what does this mean? Well, they give you bearings, and the first thing you have to do when you get a problem like this is, write down your points and start with something, and then they suggest that you draw an auxiliary line due north or straight up, and that is just a way to help you get your bearing, so you understand, all right, north is up. So again, I'm not writing this down. You should be writing this down in your notes. North is up. North is, I will put this right here in text. Let me ask Nicole over here. Nicole, what color do you want? You want blue? Okay. So north is up, which is 0 degrees or 360 degrees. Right? There's 360 degrees in a circle. Straight up is 0 degrees or 360 degrees. Okay, so now let's get back to the problem. So I've got a point A, and here's my north bearing, right? Now if I go here and I say from A to B, first I look north, I'm going due north, and then I turn 65 degrees east. Well, that's 90. Halfway between is 45, so somewhere along this line, I don't know exactly where, right? It's 65 degrees. Now, it does very specifically say it is 8 miles. So I'm going to step to the board here and mark this out very clearly that this is 8 miles from A to B, and that this angle right here is 65 degrees. Now the next piece of information, so check. I've done this first part right here. So the next piece of information I have is from B to C is north, right? And then 24 degrees west. So again, this would be 90 degrees west. This would be 45 degrees west. This is like, I don't know. There you go. We're going to call that 24 degrees west. And let's label it. So this angle here is 24 degrees. Okay, great. I can handle that. That's fine. Now, it doesn't give me an exact distance, so I don't know where exactly on this line it is, but I know that from B, post box B to the post office is somewhere on this bearing. The last one we need to look at is from C to A. So somewhere from C to A, right, up here, is south 20 degrees. So let me just get point, I guess I can move my picture out of the way. Here's point C. So C is somewhere on this line, right? Now, it says south. So let me just turn this around. Hey, there's north, and now I'm south, right? And it says point south, and then 20 degrees west. Well, what does that look like? Well, again, here I'm at C, and I go 20 degrees west. Well, again, here's 90 degrees west. Here's 45 degrees west. I don't know. Well, let's just call that roughly 20 degrees west. Now, what's so interesting about what has just happened is I don't know exactly where C is, right? I don't know where C exactly, let me not do it. I don't know exactly where C is, but I do know when I'm at C, looking back to A, it falls on this line. Well, where those two lines intersect, then yes, I do have an exact angle. The final thing to add here is, but don't I need to have angle measures in these? And you know what? These green parallel lines give you angle measures, and that's really the whole point, because all these north-south lines are parallel. So I can look back and say, oh, wait a minute. If I have transversals cutting across parallel lines, then I know using like alternate interior angles, I know what these angle measures are. So let's check this out. I'm going to mark these lines as parallel just for kicks. You guys like kicks, right? Right? I know this angle right here is, we said it was 20 degrees. Right? So this part is 20. I know if I have a transversal 60, this is 65. I can figure out what all of these angle measures are. And that is what's kind of such a cool and powerful thing about this process is, I'm not going to do it in this example here, but I can figure out what all these angle measures are because of the parallel lines formed by the north-south lines. So the last one I want to look at, let me move my picture out of the way here, is what's called angle-angle side. And again, this is a theorem because if you know two angles are congruent, well, of course, by the third angles theorem, the third angles are congruent, and then you're back to angle, side, angle. And that's really the big idea. But here, again, angle, angle, side, angle, angle, side. So what does this look like? Use angle, angle, side to prove that the triangles are congruent. And the given information says JL bisects KLM, and angle K is congruent to angle M. So let's set up our statements and our reasons, of course. JL bisects KLM. Well, what does that mean? Well, that means that angle KLJ is congruent, KLJ is congruent to MLJ. So let's just label that right now. We can just go like this. We can go, hey, whoosh, whoosh. I'll put two little arc marks here. All right, so far so good. I've got two angles congruent if I only had a side. How am I going to get a side congruence? And that's right. Sohan, you're jumping out of your seat. JL is congruent to itself. JL is congruent to JL by the reflexive property. So now I've got enough information to say, oh yeah, triangle JKL is congruent to JLM by angle, angle, side. The last congruence, triangle congruence theorem or postulate that we're looking at is called hypotenuse leg. And of course, when you use the word hypotenuse, you're referring to a right triangle, a triangle with a 90-degree angle in it. And what you need here is you need to know A, that you have a right angle, and B, the hypotenuse and a leg. And we'll spend some more time on this later on, but again, before you needed an included side, and this is an example where you don't need an included side. You just need any two sides of a right triangle and to know that it is a right triangle. So here's how it looks. Determine if you can use HL congruence theorem to prove that ABC is congruent to DCB. And if not, what other piece of information do you need? Well, by this point, take a look at the problem and you think, well, wait a minute. All these problems have had a recurring theme, and this is really the point to drive home is, when you have a shared segment between two different figures, you need to establish that that segment is congruent, and that is our first step. So CB is congruent to CB, and of course that is from the reflexive property of congruence. Now, once you've established that, you have a side and a hypotenuse, or a leg and a hypotenuse, and a right triangle. So therefore, yes, I do know these triangles are congruent from the hypotenuse leg theorem. This is probably the most important thing to get in your notes. I know you've got the theorems, but to be able to organize them and say, hey, how can I quickly identify if triangles are congruent? This is the way to do it. Make a nice table, pause the video, copy this down, put the pictures next to it, and that way you can quickly refer to this diagram when you take a quiz and say, hey, what am I trying to do? The next chapter and beyond, this stuff is not going to go away. You need to prove triangles congruent first before you can move on, and so it's nice to have a quick reference. I'm going to stop the video here and just make it into 2 videos. I'm sorry it's been so long, but really what I'm trying to do is cover 4 or 5 sections in a video. It's not going to happen, but stay tuned for the next one.